Oh, good call. All right. Okay. So, all right. So this is like the pretty standard, you know, writing of code, which is what we do is we like kind of get some rules, right? Like, you know, get the legal age of driving, and then maybe like a product manager is going to tell us the logic. And then what we'll do as software developers is translate that logic into code. Okay. And it's not, you know, it's obviously like people get paid a lot of money to do this type of skill. So, you know, it can range from something pretty simple like this to something very complicated logic that takes a while to do. But then like hopefully it works, right? And we can test our results. Now, with like what we want to do this evening, right? And what the task of machine learning is, you know, it's like how do we translate if we want to predict is this number 5, right? Or the number 9, or we want to predict like is this, you know, what number is this or any of these, right? It's pretty hard. What's different about this, I think, is it's pretty hard to write logic for this, right? To take specifications from a product manager or anyone else that has knowledge about the domain and then translate this into if-else statements, right, ourselves. Like we could think about doing it, right? Like maybe like the 5 has like a horizontal line, a vertical line, and then a curve. But you can see that this doesn't really fit by this, right? Like it's a more difficult or nebulous problem. And even determining the logic for this is complicated itself. And really what we do is instead of, you know, getting the logic, let's say we getting the logic and then translating that into code, with machine learning, we let the machine, right, somehow, you know, tell us that logic, okay, or determine that logic to then, you know, make a prediction itself, okay? So we're not going to be the ones, you know, maybe we do like a little bit of the job by feeding in certain parameters, but really we're going to be leaning on the machine to determine, you know, what makes this a 5 and what makes it an accurate prediction to determine that this is a 5 or not. All right. So regardless of whether you're doing neural networks or you're doing decision trees or you're doing linear regression, that's the same procedure, right? That's the difference, is that with machine learning, we're asking the computer or our algorithm to determine some of the logic to ultimately make predictions. So how do we do something like that? Well, this is a pretty classic machine learning problem. I think it was like in the early 1990s. That professor at University of Wisconsin, what he did was he wanted to see whether he could describe attributes of slides of cells, okay? And so this, you know, these are different cells, right, on a slide. And what he did was he had nurses, or I think maybe graduate students, write down the attributes of these cells. So he described like, okay, what's the mean cell area on this slide? And then what's the mean number of concavities on this slide, right? So people wrote by hand this. And then based on that, he also diagnosed whether or not there was cancer present, okay? And the idea is to see if we could use machine learning to find a pattern here, right? To say that, oh, okay, like when the mean area is this amount and the mean concavity is this amount, right? Then there's cancer present on the slide. And when the mean area is this amount, right, and the mean concavity is this amount, right, then there's not, okay? So the first step, the reason why I would go through this is, you know, this is an example of a machine learning problem, and the first step in this is to first gather the data and get some past examples. And notably, you know, the thing most important to notice is that we have the answers, right? We're learning from, you know, the past, what we'll call, I'll give terms in just a second, but, you know, past examples where we have the answers, okay? So each row of data, right, or yeah, each row of data here is called an observation, okay? So this we would say like this is like one slide, right? And this is the mean area on this slide. And then this is the mean concavity on this slide. And then here he determined, right, like a doctor determined that there was cancer on that slide. And this is another observation, another observation. So the set of these observations is called our training data. And the idea is that like we want to somehow like have the computer like learn from these past examples. Now, when breaking down each row of or each observation, we can think of this as divided into two components. So these are the features, right? Which you can think of like the characteristics, right, of each slide, right? The mean area, the mean concavity. But we call this the feature in machine learning. And then the most important thing is the target. So the target is what we're trying to predict, right? So we're trying to, based on these features, have a machine learning model determine or predict whether or not there is cancer on the slide, okay? So it can look at past examples and then hopefully maybe like learn from that to predict future observations where it does not know the answer, right? Because that would be really great if we could now like, not use a doctor, but rather give it a slide, describe the characteristics, the nurse could write them down, and then, the machine learning model will kind of like tell us whether or not, this slide, there's probably cancer here or there's not. So, so that's what we went through here, right? We have the observation, the target, and then the features. Now let's think about what this looks like in a plot, okay? So right here, what I did was I plotted the mean concavity and the mean area, right? So this is each dot here represents a single observation. And if it's purple, this was negative, right? Meaning that there was not found to be cancer. And if it's yellow, then it's positive, right? And we have a 1 there. And so you can see that it does seem like there's a pattern here, right? Like it seems like the larger the mean area, right? All things being equal, the less likely, right? It is that that the slide has cancer on it. And the larger the number of concavity, well, actually, the larger number of concavities, it seems like also less likely, right? Like there's some things right here, but also the other thing you can see is it seems like a combination of the two. So if we were trying to predict, like whether or not there was cancer or not on the slide based on these characteristics, well, it's like how do we make that prediction? One way to do that, let me look at the chat. Are targets only binary? Great question. They're binary in a classification. Well, that's not even true. They're binary in a binary classification problem. So in this cancer example, right? It's either you have cancer, this is breast cancer. Either you have breast cancer, or you don't, right? When you think about this problem right here, if we think about the target, the answer is either it's the number 5, it's one of these 10 numbers, right? One of these 10 digits. So here, we don't have 2 different options, we have 10 different options. So that's a classification. Both of those are called classification problems. And then in a regression problem, maybe we're trying to predict like the length of a hospital stay, right? Which could be anywhere in a range of numbers. That's called a regression problem. Or like a classic regression problem is like, let's say you're trying to predict someone's like weight, right? Based on their age or sex, right? That can be any number in a range. That's a regression problem. But here, when the outputs or when the targets are discrete, that's called a classification problem. And when there's only 2 potential outcomes, that's called a binary classification problem. So here, there's only 2 potential outputs: cancer or not, or cancer is present on the slide, or cancer is not present on the slide. So, okay, so let's think about this, right? Like we see this past data, right? And if we're like a person, right, and we're like looking at this pattern, and we're trying to make a prediction, you kind of see what I'm automatically doing. I'm basically just drawing a line right down the center. And if you're on one side of the line, we'll probably predict that there's not cancer present. And if we're on the other side of the line, we'll predict that there is cancer present, right? And that's exactly, like that's called our hypothesis function. And that's exactly what a machine learning model, including like a neural network, will do, okay? Is, this is, we'll see in a little while, this is called like a decision boundary in this case, but this is, in machine learning in general, this is called a hypothesis function. And what's happening is, it's basically demarcating its predictions. So on this side, it's going to predict that there's not cancer. And if we have an observation that falls on this side, it will predict that there is cancer. And what you can see, like kind of importantly, is that it gets some of them wrong, right? It gets some of the past training examples wrong, and it's also going to get some of the future ones wrong as well, which is fine. Like we don't expect this to be perfect, right? There's going to be a certain amount of error that generally occurs. Depending on your domain, you'll accept, a certain amount of error, and then other times maybe you won't, right? But if this is your best option, right, or if this improves your technique from previously, then you're still probably going to use it. Cool. So this is our hypothesis function, and that's the second step, right? We gather our data, we have a hypothesis function. And the way that we can tell whether or not this hypothesis function is any good, right? Like you can imagine maybe tilting this further, right? Or sliding it across. But that hypothesis function, we slid it across, would be worse, right? Because we're misclassifying more and more of our training data, right? So the way that we learn this hypothesis function, the way a machine learning algorithm determines and comes to this hypothesis function, is by trying different versions of it and seeing, a simple way would be to see how many misclassifications it makes with different versions of the hypothesis function, and then choosing the hypothesis function that minimizes the number of misclassifications. So that's called, training, right? With training, you can see I wrote it out, right? We look at different versions of the hypothesis function, and we update or try different versions of it until we come close, right? We have a hypothesis function that comes close to predicting our target data. So those are the steps, right, of machine learning. And then once we train that hypothesis function, once we have our past training data, what's great is then I can take a new observation, say it lands right here, and because it's on this side of the line, right, we'll be guessing that no cancer is present. And then I can get another one, and if it lands here, right, then we'll predict that cancer is present. So what's nice about it is after we train this thing, and get the past data, then we can feed in new data, and we'll be able to make predictions with our trained machine learning model. All right, I think that's pretty good. So that's the process, right, that we go through all the time with machine learning is one, gather the data, right? Two, try out a hypothesis function, train it, right? We do training where we basically try different versions of this hypothesis function. And then once we train a hypothesis function such that it minimizes some sort of cost, like here we said, it minimizes the number of misclassifications it makes, then we can use the hypothesis function to make predictions on new data. All right, so now let's move into actually neural networks, okay? And what we're gonna do is we're gonna go through these steps just with a single neuron, all right? The hypothesis function, training the neuron, right? You can see it's actually hard to train just a single neuron, but these are all the concepts to do so. And then probably in the next class, we'd move on to doing this with an entire neural network and the same steps, the hypothesis function and training it. And you'll see many of the ideas of training a neural network are really in a single neuron. Okay, so how do we do this with, with a neural network? How does this thing make sense? Okay, so this is everyone has to always show, right, pictures of a neuron whenever we're explaining this thing. So this is our picture. And this is, this is a neural network in a human, okay? So I forget where I got this from. I think it was Columbia. They had these pictures. And what you can see here is this is a single neuron right here. This circle is the cell body. And what happens is it takes in, let's start over here. We take in certain inputs from these things called dendrites. And we feed in the inputs through the dendrites. We say we're trying to determine whether or not there's we're tasting something. We want our brain, ideally our brain is making a determination as to whether or not there is sugar in this food, right? So it could take in different tastes and smells right over here. And then from the cell body, based on these inputs, it's going to output, right? This neuron will make a determination or a prediction as to whether or not there was sugar inside this or not, okay? Inside what we just tasted. And then maybe another neuron, maybe this guy's determining whether or not there's sugar, This guy's determining whether or not there's salt, right? And this guy's determining whether or not there's a degree of spice. And then at the next level, these things are making an output, and these neurons' outputs are actually fed in to the next layer of neurons. And then based on this neuron seeing like the sugar and the salt and the spiciness, this guy is like saying whether or not it looks like there's like tomato sauce here, okay? And then maybe this guy is based on like the sugar and the salt and the spices determining whether or not, okay, there's like cheese on this thing. And then here, maybe it's like, okay, is this thing pizza or not? And then finally, maybe where it's telling us, should we be eating this or not, right? Like, do I want to actually like put this thing in my mouth or not? So that's the idea, is that at one level, we're taking in inputs, right, that are directly from our external environment. But then the neural network is the output from here. I think it's called the axon. Right? That's going to be the input, right, to the next layer, right? So yeah, you can see that we're taking in inputs, and then so these are the dendrites, and it goes through the cell body, and then based on that, it's either lighting up or not, right? So what we do is we actually represent this. So let's focus in on a single neuron, right? So here's the dendrites, here's the cell body, here's the axon, right? And this guy's either lighting up or not, right? There either is like tomato sauce, or like there is sugar in this thing, or there's not, okay? And this is how it's oftentimes like represented, right? Is like we have these different inputs, you have the cell body, and then you have the axon. And what you can imagine is like, here's different features, right? Here's different inputs. Like before with the cancer cells, right, we had like the mean cell body and the mean area to make a determination as to whether cancer is present on the slide. This time, like in this example, we'll say, okay, like does this thing smell sugary? Does it taste sugary? And then we're going to output like a 1 or a 0 to indicate or make our prediction as to whether or not there is sugar present there. So we can translate this into code, all right? So what I can do is like we can just like say like, all right, here's like this taste sweet amount that maybe like we get from our palate, and there's like this smell sweet amount. Oh, sorry, sweet amount, and then we're going to return this value. And we can just like maybe like add these up, and so you can see like we have this chocolate taste sweet amount, this chocolate smell sweet amount, and we will pass these two inputs in, and we'll just start here, right? That we can add this up. Taste sweet amount is not defined. Taste sweet amount. Taste sweet amount. Oh, this is the chocolate taste sweet. So this is an amount like if I actually put some like a piece of chocolate in my mouth, maybe it gets this score for what it tastes like and this score for what it smells like. And then, we can imagine that we pass this into our neuron, and maybe like if it's big greater than some number, we're going to make a determination, or a neuron will make a determination that there is sugar there. Okay. So let's actually, I think like let's update that. What we could do is we could say like, what we'll do actually is what we can do is we can, beyond just adding these two numbers up, we can imagine, like that, like the taste actually matters twice as much as the smell, right? So one thing we could do is we could just like multiply this by 2. So it doesn't have to be just purely adding, right? When we're feeding these inputs in, right, we might weigh one more than the other. So we can just update our thing right here, and like we're getting an output, okay? And the way that we can ultimately use this is with an activation function. So what that means is, one thing we could say is like, if this number, right, is greater than like 23 or greater than like 10, then we're going to say there is sugar there, right? Like the sweetness amounts are such that we're going to say there is sugar there. And if the number like isn't greater, then we'll say there's not sugar, right? It just doesn't cross that threshold. So one way to do that is to say like, okay, like this number, let's call this like my sum. I'll just call this weighted sum for now. All right. This is like the weighted sum. Okay. And we'll say like, if the weighted sum, so this will give us that number like 23. And we'll say like, if the weighted sum minus some, number, right, is greater than like 15. So minus 15 is greater than 0. right? Then we'll say like whether or not we think there's sugar there or there's not. So we'll say like if weighted sum minus 15 is greater than 0, then we'll return true. I should put a parenthesis there. Do else, return false. Okay. So this is pretty good, right? Because this can like have our neuron like basically light up or not based on the taste sweet amount, smell sweet amount, right? It's going to make some determination, and then we're going to return true or false. So let's try that. So now you can see that this returns true, and if the smell sweet amount was like pretty low, right? Then let's do, maybe I need to do it because taste sweet is worth so much, right? Now it's returning false. Right, so this is actually, believe it or not, what we just did right here is a valid neuron. In fact, like up until the 1970s, this is what people would use as neurons. This simple weighted sum, right, followed by an if-else statement, okay? Or basically either we're firing or we're not firing. And this is called a perceptron, right, where we have a weighted sum, and then, firing basically all or nothing firing. That's called a perceptron. Okay, and this is a valid neuron. So cool. So we actually did all this. So this linear component, right? This is our weighted sum plus that threshold. And here I call it the bias, right? So you can, if I move this down, you can see that we have this weighted sum right here minus this bias term, right here, or it's like plus negative. And then if this weighted sum minus the bias is greater than 0, then we return true. Otherwise, we return false. And one thing that oftentimes happens is you'll actually break this up into two functions. So you'll return, this function right here, and we'll call this guy like z, or like for your linear function. And then this part right here, this do you fire or not, is called the activation function. Okay, so you can imagine that we're going to pass through z into here, and if z is greater than 0, then we'll return true. Otherwise, we'll return false. So let's just see that, right? I can do like z, then the taste sweet amount is like 5, right? The smell sweet amount, yeah, it's like 3. Z is not defined. All right, so it gives us a -2. And then I'm going to pass this output into my activation function. And because it was less than 0, right, it's going to predict false. Okay, so it's going to say basically like there was no like sugar in there. Okay, so the reason why we go through this is like our activate these, it's important just to like define the components, and then we'll make these components more sophisticated over time. But like even when we get to like our final version of our neuron, we're still going to have a linear component, right? A weighted sum and a bias. We're going to have an activation function. We may change it a little bit. And then like actually our task is going to be like to learn like what should I be weighing, when we train our neural network. What we're going to ultimately have to figure out is like how much weight should I put on like the smell, how much weight should I put on the taste, right? And what should maybe my bias be to to then ultimately be able to predict correctly. All right, but we'll get there. Okay, and this is a good way, right? You can kind of see like how this corresponds, right, to our neuron picture, because this would be like does it smell sweet? This would be, does it taste sweet? And then here we put those inputs, we weigh them, right? So it'd be smell sweet times by some number, taste sweet times by some number, plus a bias term. If this weighted sum is greater than 0, right, then we fire or we do not fire. All right, any questions before I move on to the next thing? So the next thing is just going to be updating, right? And this is a hypothesis function the next thing is going to be to update this hypothesis function. All right. Okay, so let's, oh, you know what actually we need to do? I think we need to plot this thing first. So here's from neurons. Here's the sigmoid neuron. Let me see. Let me actually go to this thing. Yeah, let's do plotting a neuron. All right. Okay. So this is what we just saw, right? And right here, right, we can download some data and plot it. And what we want to do is we just want to be able to like translate the neuron. We actually want another tool to be able to see this visually. So, okay, so let's see this. So here's kind of the same, it's something pretty similar to what we saw with our breast cancer data. Here's our taste score, right? So this is like one, piece of food, essentially. You can see it has a taste score and a smell score. Same thing here. And then same thing here. So these are different pieces of food. And then what we want to do is like, let's think about, what a hypothesis function would look like for this. That is also a neuron. So this actually works, right? It's the same exact thing as we saw previously. Well, the way that this works is we could imagine the neuron firing if we have an observation that lands on one side, and not firing if we have an observation that lands on the other side of this is called a decision boundary, right? Of the decision boundary. So, and the way that the reason why this kind of like works is you can see that if this decision boundary corresponds to this equation right here, 2x plus 2x1 plus 1x2 minus 18 is greater than 0. So this decision boundary is all of the points whereby this equation equals 0. So let's just see that, right? If I go here, right, then we get 9, 0, right? So x is 9, x1 is 9, x2 is 0. So x1 is 9, right? That's 2 times by 9. Right, plus 1 times by 0, that's 18, minus 18 is 0. Now let's just do one more. So here we have 8, 2 times, x1 here is 8, x2 is 2, so we have 2 times by 8, plus 1 times by 2, right, that gives us 18, minus 18, and then we have, if it's greater than 0, predict 1, otherwise predict 0. So you can see this line right here is just corresponding to our weighted sum, essentially, right? And this is like kind of how we're representing both the linear component and the if-else statement is just like, do you fall on one side or the other side? All right, so this is, the same thing. This is a perceptron, okay, with a decision boundary. And let's keep going. All right, and this is exactly what we did previously, right? Like this also, what we saw with our breast cancer data, this also qualifies as a perceptron, right? We have a decision boundary that corresponds this time to this line, right? And if we go on one side of it, then we predict no cancer. If we fall on the other side of it, then we predict cancer. So we can imagine this, again, like as a single neuron firing or not firing. Okay, now one thing that you may notice is that the closer we get to this decision boundary, the more we make mistakes, okay? So one thing we may want to say is like, all right, if we're like far away from this, maybe we don't want to say like, like the output maybe shouldn't just be like 0, but that like we're confident that there's no cancer here, right? Like if you think about a real use case for this, right? If we're anywhere in this region, like pretty close to a decision boundary, like maybe we should put a second set of eyes on this and tell like a doctor to review it. But if we're like, all the way over here, maybe we'll say like, hey, we feel pretty confident. And if we're all the way over here, then maybe we, want to make this really like a priority, or like, make sure we have a discussion with the patient, right? Or take different actions. So it really matters, right? We can, instead of just outputting like a 0 or a 1, what we want to probably do is find a way so that we can like express how far away we are from the decision boundary. And one thing you'll notice that we can do is instead of doing the activation function, let's define it. Instead of just like feeding the linear component into the activation function and outputting a 0, well, if we have a really high positive number, right? Because this is everywhere that our function is going to equal 0. So if we have a really high positive number, that means that we're far away from here. I guess we'd be over here. We'd be far away from the decision boundary. And we'd be, the higher this number, this output is, the further away we're going to be, right? And the more confident we're going to be. And then same thing in the opposite direction, right? Because if it's less than 0, then we're probably pretty far away from the decision boundary over here. So one thing that we could just like get a sense of is actually like if we remove this, right? Then you can see like this isn't super close to the line, right? It's negative 2.1, right? If we outputted a number like negative 0.1, well then that actually tells us we're less confident in the prediction. Like we don't know, we're not quite sure whether or not it's cancer or not cancer there. Here we're more confident, right, that there's no cancer. And then same thing the other way. So actually like by maybe changing, right, it's like we're losing something in our current version of the activation function. So that's what we want to do next, right? We want to somehow be able to like capture, I guess we're not doing it right here. Let's see if we have it here. We want to somehow be able to capture like the distance. You can see it here, right? Right now we have a large number in the positive direction. I just removed the activation function in this version. So this way, if we output a number like 4.7, right, then we're probably pretty confident that there's no cancer present. And then, or I think this was that there is cancer present, which makes sense. It's a large positive number. If we output a large negative number, then we're pretty confident that there's no cancer present. And if we're like close to 0, you can see that the closer I get to the decision boundary, the closer our numbers are to 0. Well, this is where we're unsure, okay, with our hypothesis function. Does that make sense? So this is what we want to do next, is update our activation function. So that's basically expressing how confident we are based on how far away or how either greater than 0 we are or how much less than 0 we are. All right, so let's go ahead to doing that. Any questions before I move on to that, right? What we want to do now is you can see visually, right, why we might want to like capture this distance from the decision boundary, because it really like affects, it tells us about how confident we are in our predictions. So previously we did an all or nothing output, like a 0 or 1, but that's not telling us, like, that's basically giving us the same output of 0 for this guy as it is for this guy, right? So we want to update that. All right, so let's see how we can do that. So the way that we can do that, right, remember our goal. Our goal is if we have a large negative number from let's put it this way, if our linear function outputs, right, a large negative number, right, then we want to express, confidence that it's not, that we're close to 0, right, of a prediction of 0. And if our linear function outputs a large positive number, then we want to output, then we want to express confidence of a prediction of 1, right? And one way, I think, the way to do something like that is we can do this essentially by doing something like this, where what we'll do is if we're pretty confident that it's a 0, right, that there's no cancer present, then we should output a number close to 0. If we're confident that there's cancer present, then we should output a prediction in a number close to 1. So in other words, if we do like output like a 0.99, then that's pretty close to 1, right? And we're expressing confidence. If we output a number like 0.59, the prediction is still going to be that there's cancer, but we're less confident in that. And the border, like right on the border, is 0.5. All right. And then the same thing works in the other direction. If we output a number of like 0.01, then we're predicting, essentially with the same degree of confidence here, but in the other direction, that there is no cancer. See that? So this is our goal, right? Is to update the hypothesis function such that it's not giving us like a pure 0 or 1, but rather it's giving us a prediction from 0 to 1, right? And if we're totally unsure, we output a 0.5. And if we're confident that it's a 0, we output a number close to 0. And if we're confident that it's a 1, we output a number close to 1. Okay, so that's our goal. And the way to do that is with this thing called a sigmoid function. So I'm gonna write out the sigmoid function, and then we can play around with it. So the sigmoid function is just 1 divided by 1 plus e raised to the negative z, right? And we're gonna write it out and play around with it. So I should do 1 plus, to do exponent, you just do np dot exponent. So this is e raised to the negative, so we could do z right here. This would be the negative z, and we'll return this. I need to make sure I put parentheses here. All right, so let's see this. So I'm gonna probably write out sigmoid here. And remember, what I wanna do is I'm gonna get an output from my function z, right? So we're gonna have this like linear component z that has like my smells sweet, my taste sweet, right? And then it's gonna return, some like maybe it's 2 times by the taste sweet plus 1 times by the smells sweet, right? And then we're going to get an output from here. This is going to be like maybe 2, like negative, I don't know, negative 1. Okay, and that's 0. So this guy is actually totally unsure whether or not there's sugar there, right? So what we want to do is pass this output. This is my linear output into this function. And ideally, this guy was actually going to output a 0.5, which it does. And then if I'm over here, right, if this guy's more confident, right? So here it's like kind of more confident. Let's actually make it more confident than that there is sugar there. So here's a larger positive number. Let's see what this does now. Now this gives us 0.95, right? And if it's even larger, like here's 7, right? Now it's really confident. And the same thing in the other direction. Like if I make this, this is a negative 2. Now this should probably be a number that's, pretty close to 0. Okay. So this is called the sigmoid function, and let's unpack how it works, right? So if we plug in a number, right, a large positive number, well, what happens is, remember the formula is this. Okay, so this is the formula. So we're going to plug in the number like 1,000. So this is 1 over 1 plus e to the negative 1, I'll zoom in, e to the negative 1,000, which really means 1 over 1 plus 1 divided by e to the negative 1,000. So what the hell, what does that do for us? Well, 1 over this thing, this large number, basically approaches 0. So this is going to be like 1 over 1, right? So this is going to be a number, right? 1 over 1 plus a little bit, essentially. This is going to be a number that's close to 1. So if we make this number, right, if we output a number really, really large from our linear component, from that z function, it's still just going to translate to a number close to 1 when we pass it through this sigmoid function. Does that make sense? And then with the large negative number, we feed in a number, like a super large negative number. What does that do for us? Well, this is 2 negatives here. So that's just e to the 1,000, right? So this whole denominator just becomes a really large denominator. So what does that mean? 1 divided by an enormous number plus 1 is a number close to 0. So when we pass through a really large negative number, then we get a number close to 0, right? 1 divided by like a billion or something. And then finally, let's say we output from z, we output that 0. So what happens there? Well, we have 1 divided by 1 plus e to the 0. Whenever we do like some number to the 0, right? If we do like 3 to the 0, that's always 1, right? So this is 1 divided by 1 plus 1. So that gives us, so whenever z is 0, we're going to output 0.5, which is also what we want. So that's why like the sigmoid function is really good to use. All right, so this is now like our new hypothesis function, is our linear component, right? So this is, you know, what we somehow found for that breast cancer example, right? And then we take my linear component, and I think this was like the first observation in there. We take the x1, take the x2, right? And we get this number, and then we're going to take this number. This is my linear output, right? And we're just going to pass it through the sigmoid. I think I called it sigmoid, right? Let's find out. Yeah, cool. So now just take this and pass it through here, and right, we should be able to guess. This should be a number pretty close to 0, right? Okay. So it's pretty confident, right, that there's no cancer on this slide. And when we do something like that, I might have to, this might break. I might have to do inferred dates equals false. I did it wrong. Let's find out. Oh, convert dates. I think it's that. I'm wrong. Well, anyway, if we were to plot this thing, yeah, it's not going to plot. But if we were to plot this thing, what we would do, what I was trying to show in this image, is that basically like what you're doing is each one of these points now, now instead of doing like -0.2, this will be like a number close to 0, right? Because we're just going to pass this through that sigmoid function, okay? And this is going to be a number close to 1. So the further we get from my decision boundary, the closer on this side, on one side, we're going to get closer and closer to 0. Here, we'll get closer and closer to 0.5 if we pass it through my sigmoid function. And on the other side, here will be like around 0.6, 0.7, right? And then we're going to get closer and closer to 1. And that is, right, that is like the final version, right? This is a hypothesis function for a single neuron. And this totally, you know, like there are different ones you can use, but this one works totally fine. All right. The last thing to say is so one thing, I think the last thing to say is you can think about this, right? People talk about like layers of a neural network. You can think about this hypothesis function as occurring in kind of layers, right? Because we would say like maybe this is, let's go back to like the taste sweet example, right? This would be a single observation. So this is like one piece of food. And then this is, all right, the taste sweet component, the smell sweet component. We take in this input, right? This is almost like the dendrites, right? Remember that? And then we pass it through. This is like my cell body. We weigh each component by some amount and a bias term, and we get an output from my linear component. Then we pass that output into my activation function, and now it's not going to do an all or nothing firing, but rather fire, right, a number between 0 and 1, any continuous number, okay? And passing it through my sigma function. This, like I have it listed as A of Z. Last times you'll see it as the sigma. Okay. But that's the idea, is you'll see this, like you're going to see, like as you go further into neural networks, you know, layers. And this right here is kind of describing, you know, this like the input layer, the linear component, and then the activation function. This is the linear component activation function of a single neuron. So that's the first, you know, if we wanted to go through, you know, the hypothesis function, or like all of a neuron, what we just went through is the hypothesis function of a single neuron. So I think, you know, next, you know, I guess we could practice this a little bit, and then we could go to training a neuron. All right, so that's what we'll do, you know, this in the second hour. Questions before we, like, I give you guys this lab to do? Oh, I can show you how to do this lab a bit. No? All right, cool. So so let me just show you how you can do a lab, and I'll share the link, right? Okay, so this is, you know, reviewing the hypothesis function. So we have our linear component, and then this is the activation function, right? This is our sigmoid function. And okay, so in this lesson we'll learn about sigmoid neuron by applying the problem to our cancer data set. our task is to find the value of W1 that predicts whether, oh, this is training a neuron, I'm sorry. Let's click on Sigmoid Neuron Lab. This makes a little more sense. All right, so okay, we want to build a perceptron to determine whether or not to go to like a bar. Remember those days? Let's say that the factors are the number of beers available and the number of food items. So now I'll click run anyway. And okay, so now what we want to do is write a hypothesis function that weighs beer selection and food selection equally and returns a 1 if the evidence plus a bias of -16 is positive and returns a 0 if not. So what, I won't do this for you guys, but what you'll have to do, so this is a Google Colab notebook. And in order to run, for every cell here, you need to tell Google or tell the computer that that you want to run this code. So you have to hold down the shift key and press return, or another way to do it is to press play. Okay. If you don't do that, if I say foo equals whatever, and I forget to press shift return, then the computer doesn't know anything about what just occurred. Okay. So you have to run it in order for it to be executed. And then what your task is to do is basically, you can see that we've now have this data, Tony's and Pete's, all right? And what we need to do is write a function that weighs beer selection and food selection equally and returns a 1, right? Here's the if the evidence plus bias of -16 is positive and 0 otherwise. So you're gonna have to write out something here. So just delete the pass, and it'll be all right, if 1 plus 1, right, this is obviously wrong, and then return it. And if it's right, if you did this properly, then you'll run this function, and you'll get a number that matches this. And then same thing down here. Okay. So why don't you, I'd say how many people are here? Maybe I'm gonna put this lab in the chat, so you can work on it by clicking on Sigmoid Neuron Lab, and this is a way just for you to kind of reinforce your understanding of the hypothesis function for a single neuron. And then, like I said, we'll move into training. So I just put that in the chat. And I think what I'll do, there's 18 people here. So why don't I break you guys up into, oh, sorry, Gaurav, into pairs. And then let's do this. We'll do 8 rooms or 9 rooms. Yeah, 8 rooms. So I'll create breakout rooms, and I'll just give you guys 5 minutes to go through this, try to go through the lab, and then we can come back as a group. All right. And if you don't mind, just share your screen. You'll see how to share your screen. It's towards the bottom of Zoom, and then also turn on your camera so that your partner can see you and you guys can work together. All right. So we'll spend 5 minutes or so on this. Hey guys, how's it going? Can you guys unmute? Oh, there you are.
I'm the only one here.
Oh, okay. Gaurav isn't there.
Oh, you there now? Hello.
Gaurav, are you there? You must have clicked it, but it's all right. So did that make sense, Vish, what I was going through?
Yeah, so far so good. Yep.
Okay, great. All right, I'm going to check in on the other groups.
Right.
Hey guys, how's it going? Can you give me like a thumbs up or something if it made sense? I think you can even do it on. Maybe people are taking a break. Ah, thanks, Anthony.
Oh, it's our teacher.
Hey guys, how you doing?
Not bad. Hello.
Hey. Did it make sense so far?
Sorry?
So,
Did the what I went through, did it make sense so far?
yes,
Oh yeah, you go first. It's fine.
it's good. I'm sorry, I'm not familiar with. It's taken me a little bit to get the Zoom. I'm not familiar with Zoom very well.
Oh yeah. So towards the I know sometimes this is the hardest part. Let me see.
So I think this is great, though, especially doing a workshop. I think it's a great idea. It probably is going to take us a little bit longer. Oh, there it goes. Did it go?
Oh great, cool.
Yeah. Looks good.
So we just have to write something in the linear function. So return. Let's see. So Pete's is. We want to add those two together. Let's see, Tony's.
Yes. X1 and X2 minus 16.
Well, I'll try Pete's.
Chris.
Yes. Hey, Jeff.
Hey, how's it going?
Good. Good. We're stumbling up here. Number of beers not defined. I think I missed a step.
Oh, you know what? Because so restaurant features is a little
Mhm.
complicated actually. Restaurant features is a list, right?
Yeah.
So when you pass through Tony's, what you're doing is you're passing through a list, and then you have to access, right, like the correct feature from that list,
Mm-hmm.
and then you know, like have it correspond to the formula above.
Oh, so could it be like restaurant features, square bracket 0 is equal to number of beers, for example?
Yeah, something like that. Yeah, that's the right track.
Do I need to define it up here, Jeff, or
No.
define?
So what? So we see where it says Tony's in where like cell
Yeah.
4. No,
Mhm.
below.
Oh yeah. Uh-huh.
Yeah. So what happens is, right, you're gonna pass the list through the function,
Mm-hmm.
and then you reference it as restaurant features in the cell above in 3.
Mm-hmm.
And so when you like what you access, what you write in the function, right, is going to be like that restaurant features. And restaurant features is a list. Is that list Tony's that you pass through?
Yes. Yep.
So yeah. So you want to? I'll let you take it from there.
I'm still missing like what? So where do I guess put, you know, restaurant features square bracket 0 up here?
No,
down.
right. Replace number of beers with restaurant features.
Oh, I see. Okay, that's what tripped me up.
Yeah.
That makes sense.
Great. Yeah. That's looking good.
So it's like what you said earlier about how would it know which one's which, so things like that.
Yeah, let's see. Okay.
Oh, that might be right. I knew there was something I missed.
Oh, that's odd.
For should equal 0.
I mean, wait, it kind of makes sense though. If 4 plus 8 minus 16.
Oh, yeah, that does make sense. I wonder why this is. Oh, because we still have to write this sigmoid function. Is that why?
But that should come later, I think. I'm not sure.
Yeah. No, I think you're right. All right. Let's rewrite the hypothesis
In
function.
the below example, it also says -4 for the Peach thing, so
Mhm.
probably just the typo or something.
All right. So I think here is just this, right? Copy this in.
Probably. Yeah.
Jeff, quick question for you.
Mm-hmm.
For Pete's, so it says the answer should be 0, but 4 plus 8 minus 16. Isn't that,
Because what you want to do is output a 0 or a 1. You see how this is really an if-else statement.
oh, I see.
Yeah.
Mm-hmm. Okay. All right, so this up here should have been if else, right?
Mm-hmm.
That makes more sense.
It's like a matricing.
Wait, what is my definition? What's wrong with my definition?
Well, it says restaurant hypothesis function and restaurant features, but
Yeah.
at the very top is just like a matrix.
Yeah, it's 4, like 15 and 2. So it should take, oh wait, restaurant features. Where is that?
And did you hit play on your? Well, that's like line 2 is. We might have to rewrite this.
Guys, so what's happening is this passes through a list, right? So in order to access, so remove the word pass. You see where it says hypothesis function?
Uh,
Where it has the number 10 next to the cell? Yeah, remove the word pass. All right. So restaurant features is a list that's being passed through. So you take Tony's and Pete's, right? And
Yes.
then when you see in line 7, what happens is you pass through, that's all right, you pass
Yep.
through restaurant Tony's, which is a list, into the restaurant hypothesis function. So restaurant features, right, that argument, if you just write in below, in the line below, where it says like, instead of x1, yeah, that's fine. Why don't you replace x1 with restaurant features.
It's not working.
oh, I copied the cell.
Oh, I tried. Oh, I see. Hit paste.
Yeah.
Return. Oh, I'll just type it.
So it would be, okay. So you can do, that's an entire list, right? You see it's both like the number 4 and 8. So if you want to just grab like the number 4 from there, you would do like restaurant features,
Oh,
square bracket 0, right?
I see.
Yeah, square brackets. Great. Cool. So now you're just accessing, right, like a particular feature.
Yep.
Yeah, cool. Yeah, and you're right. I'm probably going to update this lab.
Sorry, when you put 0 and you're calling something, is that calling Tony?
No, so
Is this the first one?
Oh,
Yeah.
this is, yeah,
Go ahead.
I see. So yeah, this goes into here, and it's a list or a list, and I forgot how to access the list, but you access it by giving it its location on the list.
Yeah, so it's a little, so if you look at
Now it
line,
should work.
to follow along here, if you look at like, yeah, exactly, that line, what's happening is you're passing Tony's into this function, restaurant hypothesis function, right? And Tony's is a list that like square bracket, right? It's a collection. So then that list gets passed into your function above where it has the 17. So it gets passed into your function and you access the first element from the list by doing square bracket 0. And you access the second element from the list by doing restaurant feature square bracket 1.
So how does it know it's Tony? Like, so you're saying
Yeah.
like it passes on the two numbers that are on the list, right?
Yeah,
So how does it know
here.
that it's passing Tony?
Here's where you know it's Tony's,
Right.
by passing Tony's to your function.
That's right. You see
And
that? So
it's
you
working
can,
now.
so you can switch in. So you see in the next line, then you pass Pete's to your function. So it's dynamic, right? It changes. What you're passing through is determined, you know, when you execute the function. It's a little complicated if you haven't seen it before, but basically like that restaurant features changes. The value of it changes based on what happens in lines where the cell is 20 or where the cell is 21. In 20, it points to Tony's. In 21, it points to Pete's.
Wait, sorry, can you repeat your, so 20 passes to Tony. Sorry, your screen is a bit
That's right.
too small. Let me look at my,
So that where I'm highlighting there, that's where it got passed. So Tony's takes up here from line, how do I say the line? Well, from the top line, Tony's is defined in the top line. It's a list. Is list correct? And Pete's is defined up there. And so you defined a function that's going to take restaurant features. That's just like a placeholder, like an X. And it passes it inside this function, and this is what it does to it. And it picks the first part of the list and the second part of the list and adds them together and subtracts 12. And then down here, you run it. So you do restaurant hypothesis, and then you type in what you want to test. You could test Tony or Pete.
Yeah, that's great.
I'm not sure. So where did this 5 come from?
Oh, that's when it runs this function. So it takes Pete, well, in this case, it takes Tony's, and it adds those two together using this function up here that we defined.
Yeah, so how did you get 5? Isn't 15 plus 2 17, and then minus 16 is 1?
Yeah, I'll have to check my math there. It should be correct. So well, we're taking 0, which is 15 plus 2, so it's 17 minus 12.
Right.
That's right. It was 5.
Oh, it's 12 there. I see.
Yeah.
Yeah, and the equation is 16. I get it.
Oh, yeah, he shows 16, but it's, I guess whatever you're just trying to separate it into, that'll work too.
Mm-hmm.
You're trying to separate it into 1 and 0, or less than 1.
All right, guys, we're going to come back as a group now, and I'll review this a little bit.
Okay.
All right, cool.
Yeah, I know I'm muted. I think that one of the harder things about that lab was actually more like coding than like the neural networks concepts. So I'll like share my screen, and we'll just go through it for a couple minutes, and then we'll move on to training. So what's happening here is, right, we're defining two lists, right, Tony's and Pete's. So I'm just going to press Shift Return, and you see like this is what we're trying to define, right? We're trying to define like kind of like that neuron, right, that perceptron that either is going to output, you know, a 0 or 1 based on like these attributes. You can see like this is supposed to represent Tony's bar, and you can see like it gets a very strong rating for beers, but not for food. Okay, so the first element represents beers, and the second element represents food. And then same thing here, this is Pete's, and the first element, right, represents beers, and then the second one represents food. So let's move this down actually. Okay. The idea is that, and this is where I think things got thrown off a little bit, was with how functions work, which is, it's admittedly a little tricky if you're not used to it. So what happens is we're going to define a function here, right, called restaurant's hypothesis function. And what happens is if I define a function, right, like 1 + 1, right, and I press shift return, you can see like nothing happens until you actually execute that function down here, right? And then what's happening here is we're also passing through data. So we're passing through this list to the function. So now I'm just going to return, let's just return restaurant features. You can see that like the first time we get Tony's, which is this 15 and 2, the second time we're going to get like, represent Pete's, which I guess was 4 and 8. And then the next task to like turn this into a neuron is to say, okay, well, let's like select the first feature from Tony's or from whatever we're passed through, like whether or not we pass through Tony's or we pass through Pete's. We're going to try to make a determination as to whether or not like we should go to this bar or not. Sorry, I'm looking at the chat. Yeah, it does take time. Okay, so we select this thing, right? And now this is just printing out the first, the first element in the list. And then the next thing we want to do is like kind of get to this, turn this into this formula right here. So we do restaurant features bracket 0 plus restaurant features bracket 1 minus 16. That's starting to look pretty good, right? Maybe not. Maybe I lied. Oh, I get the number 1, but I bet you this one breaks. All right, so this is not totally right, So what's happening is, remember, we're supposed to like translate this into an if-else statement. So like if this number is greater than 0, then return 1. Otherwise, if this weighted sum, or it's not really weighted in this case, but if this like sum plus minus 16 is less than 0, then return actually 0. So okay, so we have this guy plus this guy minus 16, and let's say this is like, my our sum, or like, let's call this like the restaurant sum. Okay, we can just like return. We should spell it right? All right, so we're just returning that restaurant sum right now. And now we can put in some if-else logic that like if restaurant sum is greater than 0, then return 1, right? Like if this thing is greater than 0, then return 1. Otherwise, return 0. Okay, cool. So that's a hypothesis function. And then the next thing, we'll just do it right here. Say instead of having this being a perceptron, we want to move this to be, a sigmoid neuron. Okay. So what that means is that we should probably call this now. We should think of this as 2 parts. This is now just my linear component. I know I'm deviating from the lab now, but that's all right. We'll return this, okay? And maybe like this is a weighted sum. Like maybe we care about the beer twice as much as we care about the food, all right? So we can, and I should put the word return here. So now, based on like these attributes of the amount, the beer score and the food score, we're gonna get different numbers. 2 times restaurant features. Here's restaurant features. Here's my restaurant sum. Tony's is 15 times by 2 is 30 minus 2. So this shouldn't. Oh, because this is called linear component. Right. There we go. And now we'll do this one too. Right. Okay, so I guess this guy's right in the middle. And now remember what we want to do next is to turn this into a sigmoid neuron. We want to take this linear component and pass it, the output of that, into my sigmoid function, which I didn't define yet. So let's go ahead and do that. So remember, the sigmoid function is going to take an output here, right, which we're going to call z, And then we're going to return 1 over 1 plus np.exp. And this is probably pretty hard if you haven't used NumPy before. Right? Okay. And I think, I might have loaded up NumPy for you guys. Maybe not. Sorry about that. So now, okay, so this is kind of the goal, is that we output this linear component, which right now is giving us 16, but this should really translate into a number close to 1. So let's see if that works. So that works, right? And this Pete's, here we got, remember this outputted 0, so that means that we're right on the threshold, right? We're right on that boundary line. So this should output a number now when we pass it to our sigmoid function, close to, actually exactly equal to 0.5. Okay, so that works. All right, so that's training, right? That's the hypothesis function for a single neuron. What's more interesting, and maybe I'll even switch around the order of the lessons soon, is how do we learn? You know, like how do we know? You know, like what values this? Like how do we know that whether, you know, if I'm predicting, like, you know, the cancer example is maybe a little bit better. If I'm predicting that there's cancer or not, right, based on these features of mean cell area or the number of concavities, right, on the slide. Like, how do I know, you know, what to weigh the area by, and what like number of concavities, how to weigh the concavities feature, and then like if the combined they're greater than some number, then I'm gonna, you know, get closer to predicting that there's cancer there, and and if they output a different number, get closer to predicting that there's not cancer. Like, how do I learn this? All right, because that's really that's really where the value comes in. Is like, we kind of said this from the beginning, is that we want our machine learning algorithm to tell us the logic, right? And the logic, you know, with the breast cancer example is like, all right, well, how important are these different features and how do they combine to make a prediction? So that's what we need to get into next, is like, how do we actually learn these parameters? So that gets into training a neuron. This is pretty fun. So you can see this is what I'm doing. I'm just going through this example of like the mean area, the mean concavity is cancerous, right? And here's, you know, we pass through the linear function, the area and W1. So this is, again, like my hypothesis function. This is the linear component and the nonlinear component. All right. And then here, the sigma z. So right here, let's think about this. All right. So now we're ready. So what we want to do, right, is we have this thing. And what I'm doing is, it's like, I should be able, you know, to take an area. This is my, you know, we have an observation. We're just going to take, you know, let's just use one feature. So we're going to have a cell that has the average area, the mean area on the slide is like 1.01 like centimeters or whatever it is, right? And now somehow I'm going to pass this through my hypothesis function. So I'm going to take this area, right? Multiply it by this value W2, about W1, right? Output it through my linear function, whose output then goes to my sigma function to then make a prediction. And what's cool, like, because we don't know that 2 is the correct weight here, right? That we should be multiplying area by the number 2. So really what we want to do is like maybe try different ones. And you can see that if I try like different weights here, right, I get different predictions. Okay. So how do we know like which weight like my hypothesis function should really be using? Well, remember, this is training data. So what we could do is like, here's my areas, but I also have the answers, right? I also have like whether or not it was cancerous or not. So if I have this parameter here, like -1, right? And it's going to output a number 0.268, right? It would be great if the output was like a 0, okay? Because it's predicting 0. It's predicting something close to 0. So it'd be good if that lined up to what it actually was, right? If we change this so that it was like the number 3 here, then it would, this doesn't look so good anymore, right? This number 3, because it's predicting 0.95, but the real answer is 0, okay? So this is for a single, we could actually, before we move on, let's formalize how good or bad we are doing in predicting the actual value, okay? And the way we can do that is we can basically say, okay, like take the actual value that we observed, right? And subtract from what we predicted, okay? So here, is that right? What do we predict here? We predicted 0.95. We had a 0, right? So it's a negative 0.95. So we want this to represent how far away we are. And like if we're far away in the negative direction or we're far away in the positive direction, both of them are bad, right? So what we want to do is we want this number to always be positive. That way, like if we have, because eventually what we're going to do is probably add up how bad we are across not just one observation, but all observations, right? And we don't want, like far away in the negative direction to cancel out with another observation where we're far away in the positive direction. So we don't want like a negative 0.95 and a positive 0.95 on a different observation to cancel each other out. So what we should do is square each one of these, right? Square our error. So this is how far away. This is my actual value. This is my predicted value. And this is because I want this value to be positive or to always be positive, right? I'm going to square it. Okay, and this right here, this is called the squared error. And that's my loss function. Okay, the squared error is just y, what we actually observed, minus the hypothesis function, right? Which in this case is sigma of z of x. All right, squared. Okay, so that's my loss function. But this just tells me what this is doing right here is this is doing a pretty good job, right? Because I can imagine like as long as this thing gets closer to 0, right? I know I'm doing a better job of, have a parameter that outputs a prediction closer to what I actually observed. So let's just see if maybe I can do a little better, right? So that's pretty close to 0, right? Like, all right, that's even better, right? So I can like minimize. The goal is to try different parameters out, and we're going to improve upon this procedure, but such that I'm minimizing this function, the output of this function. But what you might notice, right, is that, well, this is just telling me how well I'm predicting this single observation, right? I don't want to like derive my whole formula based on one observation. I want to do it based on like my whole training data, right? A lot of observations. So how do I do that? Well, we just go through all of them, right? So what I'm going to do here is I have my areas, the mean areas, and the mean targets, okay? And then here's the paired data. So I pair up all the data. So this is like the mean area for this on this slide, and the mean area in this slide. See, these are all non-cancerous, but then we do have some cancerous observations as well, right? So we're making our prediction just based on one feature right now. All right, so we have each of these pairs of data. And then what we can do is here we calculate the error, right, on a single observation. But we can perhaps, I'll remove the word sum for right now. We can perhaps do this on all observations. So if I do sum of squared errors, call this function, pass through all of my paired data. This is my W1 parameter, right? This is the weight I'm using. So previously I used W1, I forget what it was, -2. Let's just use -2. And -2. What this is doing is this is now going to go through every observation, the feature and the target, in the list of paired data. It's going to calculate that loss, right, for each one of them and return a list. So let's see that. So we have, this is the loss on the first observation, and this is the loss on the second one, this is the loss on the third one, right? If we change this, right, to do something else, like 10 or something, right, we see way different losses. Actually, these are all like I'm making bad predictions on all of them. That's probably not a good number. Let's do a 0.5. And if I want to aggregate these, if I want to like summarize how good or bad I'm doing across all of these observations, I can just sum this up. Okay? So this is my total cost. Oftentimes you represent with the letter J. And this letter J, this total cost, right? Like how far I am in total from each of these observations with this parameter, right, changes based on what this parameter is. So if I did like a point, let's do like a 0.8, right? So currently I got, 151 when I did like a 0.5. That's my loss there, or we'll call this my cost. When you do it for all observations, you call it the cost. And now, now let's change it to 0.8. Now let's see what we got. Here we got 159. So this is worse, right? We want this thing to get close to 0. So maybe let's move in the other direction. Let's do like a 0.1. All right, so this is better, right? This 0.143.49. Okay, and what we could do, instead of just like me trying, going through one by one, what we could really do is we could actually like initialize a bunch of weights. All right. So here I do it between -2 and +2. All right. And what we could do is try them all out. Go through, loop through each of these weights, and then record the squared error for each of these weights. Right. So let's see that. Right. So you can see, like, as I do a negative, I think I start with -2. As I do a -2, I get 187, then 183, 179. And probably what makes sense is actually to plot these, So let's do that. See, this is more fun than the first part. All right, so we plot this, and this is pretty cool. So let's explain what this is showing. So when I have a -2 as my W1 parameter, we get a cost of 187. And in and of itself, like 187, it doesn't matter what that number is. What matters is that it's higher than the next number. So this is better, right? We want to minimize my costs. So you can kind of see right away the minimum of my cost, right? When I plug in like a 0.2, okay? When I use a W1 of 0.2, the sum of the squared errors, right? So the squared error across every observation in my training set is a 140, which is lower, right, than it seems like than every other value. So if I keep moving negatively, then I get far away the other way, right? Okay. So what I should do probably is choose this guy because this does the best job. It's the least wrong. It's the least bad out of all of my options. So I should choose a 0.2. And what you can see is, like, if you use sklearn, and use their logistic regression function, and we take in the areas and we take in the targets, we call model.fit. So I'm going to train the function, and then I'll call model.coefficient. We see we get a number. So here we got like -0.2, and actually you can see it's pretty close. -0.3 gives us a cost of 140.95. -0.2 gives us a cost of 140.95. So this one's actually a little bit lower, the 0.3. And you can see that that's reflected here, -0.26. So this was our procedure. This is, kind of baby gradient descent. We'll do the real thing in a minute. Is we start with a random value for a parameter. We evaluate how well, right? So we just chose like -2. We see how well, using this parameter predicts our training data. And then we keep updating, right? We keep trying different values. Right, we stop after a certain number of tweaks. So like here, we just did 20 of them. So the question was like, share this Git, through the GitHub. Everything is right here in the neural nets, Jigsaw Labs neural nets. So this one right here that I just did is the next lesson, training a neuron. So they're all available. So let's update this procedure. So does that make that makes good, sense, right? So far, it's just trial and error, okay, for this thing.
Sorry, I have a question. So in all these examples that you've given us, I understand like the fact of like you're trying to get to the closest, I guess, model as possible, but the equations were always provided to us. So how do we normally gain these equations? Like you had a model, I said like, okay, well, maybe like you take in one value, take in another value, and then hopefully it'll be 1 or 0 or whatever is closer to this particular number will be the best. But then at all those times, it was as if like, I can like go to my boss and say like, hey, what's a good prediction about them doing right? Well, revenue seems to be a good idea. So why don't we just choose like, you get what I mean? Like, so why is this called machine learning versus me like looking at like a number chart essentially?
Okay, well, I heard two different questions, I think, there. For the first question I feel like I understand pretty well. It was, it's like, one good question is, well, how do we know to use, like here, I kind of like, I guess I'm able to like know in advance that mean area and mean concavity is good at predicting cancerous or not. But how do I know to use these features? Is that the question?
Yes, and like how, like, I guess the question is like, how did these equations even come about? It's not more of like the sigmoid equation I'm concerned about, because that had a general purpose, but like you're saying like, okay, well, my model predicted this, and then I'm like, okay, so how did you predict this model? It's like, oh, I just used this equation that I just made up, and it just made sense to me. But how would I explain that this equation would make sense to other people? Like,
Got it. Yeah. So okay. So cool. So here's two things. One is this is like, what you do in machine learning is you try to think of like what's it. So if you look at like the job descriptions of machine learning, right? A lot of what they'll be asking for is not only to know these equations, right? But also to have like what they'll call as like soft skills. All right. And the soft skills is to be able to consider what is everything that could be going on. And then to be able to get, not only to like consider what could be explaining this outcome, but then to be able to gather that data, right? Like this is where models go wrong, okay? Is if you kind of breaking down the problem, aren't able to consider like what's really occurring, right? Or what could be explaining an outcome. And then the second thing, is like maybe you can consider it, but you can't get that data. So it's too hard, right? Well, okay, so that's one thing is like there definitely is like these soft skills, and like data acquisition is like a crucial part, right, of machine learning. And if you don't have the right data, right, your model can, not be predictive. So another thing to say is like, okay, well then like, one thing to point out is it's a good idea to try to include like lots of different like components, and really like lots of different features. Like literally, so we do a lab of like predicting housing prices for like Airbnb listings. And like we start with about, I think like 500 different features. All right. And what happens is what's good about like doing that, about trying to be super inclusive, is that if you get a weight, say we get, you see this coefficient, if this coefficient is effectively 0, or say it's like super close to 0, it's not having an impact on your hypothesis function. And what that's telling you is that it's not impacting your it's not impacting your predictions. So it's actually not necessary. So that's called like feature selection. And so that's like kind of one technique, is to look at the coefficient, right? And see, you do something, it's not that quite that simple, but feature selection, right, is a really important like process, right? To be like, okay, well, this is really important, but this actually doesn't seem to be impacting the model. So that's one thing. But then the other thing is you want to verify your results. So right now, what we're doing is we're training the model, and we're seeing like, okay, well, how well did this line up to predicting whether or not something's cancerous, okay? But the problem with this is that we already have the answers, okay? Like we already, like how do we know that this wasn't just like a coincidence that mean area happened to line up, right? And here it also happened to line up, but actually like, in the future, maybe, one example I always give is like, if you think of like predicting, the outcome of like a basketball game or like a football game, let's say, like you could like look at the past and be like, oh, cool, like the Raiders won like on Halloween last year. So why don't we just have features like in the year like 2019, when is Halloween, like the Raiders are going to win. And the reason why, so the way that you test whether or not your features and your model is any good is you then say, okay, now try to use that same model on data that your model has never seen before. So if we were able to say like, feed this through our model, and our model is like, okay, cool, like based on like when is Halloween, the Raiders are going to win based on let's say it's 2019 data, then we only do it a good job if the model can replicate that finding on data it's never seen, like 2020 data, or say we've only fed it 2018 data, so then we feed it 2019 data. And if it's really bad at predicting the 2019 data, then we know we can't extrapolate it into the future. Okay, so that's called like training. That it's actually generally you split up into training set and like test set. All right, so that's like a holdout set. So those, you kind of asked like two good questions, which is like, how do you generalize this? So that's two things. And I think you also asked the third thing, which is like okay, well, can you explain, like, how important is explainability? Or it seems like explainability is really important. And the answer is sometimes explainability is really important, and sometimes explainability is not really important. So more and more being able to explain like how the explainability is becoming more important, but just remember our example. Let's go to this issue of predicting handwriting, right? Because this is what deep learning is used where lots of times, or is like favored, where actually like explaining the features is not so important, okay? Or is like secondary, but rather making the correct prediction is more important. So an example is, this thing where we take in an input and we have to predict whether or not this is like the number 5 or the number 6 or number 7. Lots of times, like the post office uses this when you write letters and you write addresses. They'll like basically scan in it and use a machine learning model to translate that into an address, right? So they'll do handwriting recognition. They don't really care how it works, like they're like you have to make sure that like it's good not only in the training set, but then also like in the future, like we're accurate, right? Like we're on future data, but it doesn't care really how it got to this answer, so long as it gets there correctly, right? So that's like a model that's not very interpretable, but is highly predictive. And sometimes, especially with neural networks, like that's the type of problem that you oftentimes use neural networks for. Like another would be like voice recognition, or like your face recognition, right? In your iPhone. Like you don't really care how predictive it is, or how to explain it so much. What you favor more in that example is prediction, right? And I'd say that's like, like I could definitely hear like a counter to that. Well, wait a second, like what if it's using really, unethical things or things like that? And that's becoming more and more of an emphasis of machine learning. And there are techniques for you can like take a look at like which observations it does a crappy job on, which observation does a better job on. And there are like, so people are developing techniques to increase model interpretability.
Got it. that was a lot to take in. Yeah. In terms of like you're saying, like sometimes it matters, sometimes it doesn't. Like I remember there was a time when there was a facial recognition and they couldn't like recognize Black people. Like not to be racist or anything,
exactly,
but like,
right? Like that's done all, like for instance, like another typical example is like loans, right? Like you can imagine, right? Like so like poorer neighborhoods, they may, or like certain minorities like Black people, they may you might develop a model that is saying, oh well, like in real life, like we'll just use, we'll train the target. Our target will be like what our employees use to grant a loan or not grant a loan. And if the employees are discriminating based on somebody's skin or somebody's sex or whatever, the model is just going to follow that if that's what you choose as your training data, right?
I see.
So that's why like there's like a whole topic now on like data science ethics as well. All right. And also that's why like model interpretability really matters, because you want to check to make sure, like, that's why more and more, like it's, in the past couple years, people, if you ask like what was the most important topic in machine learning, people would say model interpretability. They've gotten better people have developed techniques that are better at debugging essentially a machine learning model. But some techniques and neural networks are kind of like famous for it are more of a black box, like in terms of how they determine the parameter, how they determine what's important.
Sorry, like this is like going on a tangent, but like when I like was assuming like machine learning and data set, it was like without the use of human help. And I thought that was the reason why it was so profound, because like sometimes like we might not even realize that we're doing something that's not ethical, but then a computer would be able to decide that for us. And now it's kind of like, hey, I have a model that works. And then you're like, great. But then sometimes like it'll cause a fire or something. Like I don't want that to happen, right?
That's exactly right. So that's why, so this actually, I think we're going to probably, what I want to get into now, we only have like 15 minutes left. So what I want to get into now is a little bit of like the job market actually for data science and machine learning. Let me show you, because it's really interesting how it's changed and what it's about right now. Because you're kind of really touching on that as well. I mean, one thing, so what I did was I went, I teach this data science program, and so at the end of the program, we're not done yet, but the goal is everyone who wants a job, like if I admitted you into the program, you should get a job, right? I come from Flatiron School, and that's the outcome that you're delivering. So, as part of that, both when I developed the program at Flatiron School, and then again, when I developed it for my own program, I'm talking to data scientists all the time, right? About like what skills they're looking for and like how to make people really eligible. All right. So let me just, this is how I'm going to spend the last 15 minutes, is just going through the job market. So if some of you guys, came here just for the neural networks part, I'll probably do another lesson next week. Just check the meetup to see that. But yeah, so this is how this, what happens. So I'm gonna just like kind of tell you guys my students' journey. So we'll go into presenting. Okay, so for the past 6 months, actually like 7 months, my students worked on data science, and they did quite well. So this is like a couple students, right? This is like Campbell, who's one of my students, and for his final project, he wanted to he's not job seeking, and he has to do like essentially a Kaggle competition where they predict if there's oil underneath the ground, and he's ranked 4 overall out of like 200 teams. And then there's another guy, Bill, who he had to predict whether or not like Walmart, different sales for Walmart, like the number of sales for different products in different Walmart stores each day. And he did really well on that. He ranked like 4% overall. And like even that, with that, I'm basically shifting the course away from data science because of us to a different topic called data engineering. So the reason why is a couple of things. One is like if you look at the number of applicants, right, for data science positions, the market is flooded with them. All right, so you can see that this was just from like a couple of days ago, and this is not atypical at all. This has been up for 3 days. There's 315 applicants, 3 days, 413 applicants. If you go and like look deeper into LinkedIn and just focus on entry-level positions, you'll see that a lot of them, there's 263 in New York, and then this amount remotely, right? But a lot of them are not actually for data science, okay? When you look at the real title there, okay? And then the other thing is that, when you get there, they're not totally entry level. They'll last for like years of experience, and like that you have a PhD. Okay, and this is basically like what I heard when I spoke to different people, was that, okay, like there's tons of people asking how to become a data scientist. Like, I pinged this guy Pranjal, and we spoke for about an hour, and he was, just mentioned this offhand that like, I responded to you because like you run this school, but generally I get like tons of different messages about this and I can't respond. And you just see this. I spoke to this guy that used to be at Uber, and he said, okay, well, you basically just have to like, even if your students are great, they basically have to like network like hell to get a position. And then here's the other thing. So this is where that soft skills comes in. Like if you look at the skill set, it's both Python, statistics, SQL. So there's like the hard skills. Then here, look, like communication, right? So that kind of soft skills, talking to stakeholders, right? That kind of soft skills. And this is in 20% of the listings, right? They're asking for this. Communication in half the listings. It's there, right? What's really important, what you won't hear here, probably because it doesn't translate as well, is like making sure you stay on task, essentially, like making sure you're actually asking the question that provides value to the company. That's something like data scientists steer like off of, especially juniors a lot, and like business people have to kind of always steer them back. So that's how they and there's not a lot of, it's such like a fluid position that you as a data scientist kind of have to have that discipline. So what they're asking for in these data science positions is really, a combination of these skills of getting the data, like object-oriented programming, Spark is for big data, but then also these soft skills. Visualization is another soft skill, right? Can you communicate? Figuring out what the problem is by talking to stakeholders, and then knowing the actual algorithms like scikit-learn, deep learning, things like that. Here you can see the word metrics, right? That kind of comes into, are you optimizing the right thing, right? Like that business background. So the recommendation, and it's not like my idea, is really to go into data science or to go into machine learning engineering. Don't try to get all these skills at once, because what happens, especially, and this is like, the standards has really been upped in just the past like year or 18 months, is that it's really hard to master all of these skills immediately, especially when you don't have on-the-job training or you don't have job experience at them. So what I recommend, in the way that I'm, updating the program and, just emphasizing with my graduating students, is the engineering skills. So this is what Vicky also recommended is, it's much easier to come into data science through the back door, starting out as a junior developer, DevOps, and perhaps most relevant data analyst, then applying to the same 5 jobs as everyone else. You're learning the critical IT skills that will be important, right? So this is the career path of like tons of people, right? You can see data engineer to data scientist, data engineer to data scientist, etc., right? And data engineering is it's about 4 times as many positions across the board as data science, right? And even more, a lot more than data analysts as well. And this report has said 10 times as many, but this was me looking on LinkedIn. This is about what I found, was about 4 times as many, and they're actually available. So this I heard both by talking to people, right? Like, and then also by looking at LinkedIn and also, as well as other reports. As you can see, in terms of under 10 applicants, right? There are a lot of positions, if you go on LinkedIn, they'll have like just a couple of applicants there, and they're actually for these positions, which is nice. So then, and the salary is good, right? It's maybe a little bit lower than data scientists, but you'll see, you saw before that it's more of an entry level, thing. It's something that you could then make the leap into machine learning engineer or data science. But here's why, to me, it's very attractive. If you haven't had a technical job before, you're not you haven't been an engineer. It's a fixed set of skills that are more related, right? And that you're going to need to become a data scientist. So having good Python skills and knowing object-oriented programming, knowing SQL, right? Like at a professional level, extract, transform, and load, pulling the data and then transforming it so that it's more usable and putting it into a database. Flask, AWS, and Docker. So this is like deploying a model, right? Testing the code. Like these skills weren't as emphasized a couple years ago, but people realize like, oh, data science is code. Like you're writing code and you need professional level code. So if like we hire people that can do that, like they're providing a lot of value. And then like getting the data and having that data stored in different databases and different kinds of data, like streaming data, and then making sure that we're automating the process for grabbing that data. Well, these are all really important skills. And you can see that like this is the list, right? And it's a shorter list. And I've even, instead of including, before I included like top 8% of skills, this is down to top 6%. And you don't have to learn all these languages, Java, Python, JavaScript. Just learning one of them is fine. So this is kind of my recommendation. The path that I'm putting students on is to focus on the data engineering skills. And this is what I'm teaching in the next semester, and I've just added on these skills on this previous one. To get the data engineering skills first, right? Python, OOP, ETL, Shell, Flask, Docker, Kubernetes testing, Airflow, Spark, Kafka, and then then you can add on, right? Like the scikit-learn, statistics, right? And you're ready to make that transition, a year, 2 years later. But yeah, people are looking for all of these skills now to be a data scientist. And if you talk to data scientists, they'll actually the thing they'll emphasize most is the soft skills, like really breaking down a problem, thinking of everything that can go wrong in your model, thinking about all the assumptions that you're making that could be wrong. The thing is, the reason why I'm not emphasizing that quite as much in the course is because it's hard to show, and there's so many applicants right now that it's hard to get that through that initial gateway, which is generally like the HR person, to show like, okay, like, here's the skill set. Whereas, with there are just fewer applicants, right, for the data engineering position, and it's easier to show that skill set that you like, here's the project, here's the skill set that shows that you have, these skills, and there are just fewer applicants. So you're more likely to get to someone who can actually evaluate them. And there's actually a good demand and a shortfall for the data engineering position, where there's actually more for the data science position. So that's kind of like what you need to be a data scientist, and a path that, regardless, like if you do want to be a data scientist, this is the path I recommend, like regardless of what you choose, is focus on this skill set first. Any questions about that, guys? Like any questions about the job market? This is something I've really been studying over the past couple of years. But then, I've really come to like this conclusion. I've been seeing this more and more over the past 4 or 5 months or so.
I really agree with what you're saying. I was on job market like a few years ago. My background's academics. I got a PhD in agricultural modeling and such, and so I had a lot of math and algorithm skills, but very poor programming skills.
Mm-hmm.
And I looked out there in the data science market. It's exactly like you said. I mean, programming really comes first. It's about, I don't know anything about computer science and production, like production systems that are out there. That was my weakness. So, well, basically I stayed in academia, but if I wanted to cross over, it's exactly the programming skills that I would need to practice. And I think there's both sides of that. There's the programming. You definitely need the programming skills to work in industry. And then on the other side, I think there's a lot of people out there in academia and such who do have like, quote unquote data science, like you're working all the time with statistical models and such, but your programming is really poor. You might like in my case, I write like a R script or a MATLAB script, and that's it. So I can write a script, but putting that in production or including it or doing that really fluently and with like Git checks and all that, I don't know the programming tools. So, and I saw that when I was looking at the job market. I didn't have, that was my weakness.
Yeah. So which part? That sounds like what I was saying. And maybe
I was agreeing with you, so I was just kind of repeat how
you agree.
what you said.
You don't agree.
No, I totally agreed with everything you said. And what I was trying to do is I was trying to illustrate it with my own experience.
Yeah.
I think a lot of people that see data science are often coming from an academic background.
Yeah.
Have all of the math and statistics skills, but none of the good programming skills. So that I can't really I can write a script to do a model in R or MATLAB,
right?
But it's terrible programming.
I was just going to say the word R, right? Because I look, if you look at this, 98% of data science jobs are Python, talking about Python, and now here's where R is.
If you're in academics, you're probably using R. That's exactly statistics.
Right. That's 100% correct, right? Like you see R either with people coming from academia, or less times like some finance positions, you used to see it more because they were people that came from like this econ PhD background or something along those lines, where it was used. But in terms of integrating, right, like with actually getting data, from like internally or, from the web, right? Like Python is what you use. And for that, like it's, these, and these different technologies to actually gather data. So it's really interesting because if you look at a lot of programs, like even like university programs, bootcamp programs, a lot of them are like, oh yeah, we teach both R and Python. To me, that's way behind the market. Because you can just look at the numbers, right? I come from a software engineering background, so when I was teaching data science 2 years ago, these programming skills were not as strongly emphasized, but it didn't make sense to me. Why not? Because I was like, data science is just code. Like we should be testing each line of it. Otherwise, there will be errors, just like with all code. And now more and more, like now they are basically enforcing those requirements and bringing that into data science, which I think is a good thing.
One of the reasons I think the market's flooding is a lot of people that have the academic background, which is a lot of these models and such, and being able to write a simple script. But I think it's different between writing a simple script and being a fluent.
Absolutely. Exactly.
Like computer science and such.
Yeah, exactly. Like you need to be able to work in a large code base, right? And that's the skill, like work in a large code base, and that's where problems occur. Is when you get to like like the code base I worked in, had literally like 1.5 million lines of code. Data science code base probably doesn't have that amount, but a lot of the data, like being able to navigate a large code base and be like, okay, well, this is where this data is coming from. This is the transformation is being made when it's actually stored in my database here. Right? Like that's pretty important to understand. And then being able to write code so that every time you get a new task, you don't have to reinvent the wheel. Like that's where a larger code base comes in. So yeah, like that's what, like you'll hear, what the phrase is like reproducible data science or something like that. What they're talking about is like professional level code, such that like when you do it once, you can still use it up into the future. And if someone says, well, how did this thing come about? Or, we need to reuse this, or there's a bug here, we need to change it. You're not starting over, right? Which I think is what a lot of people were hearing or talking about a couple years ago. Any other, so just to tell you, give a plug for my program, it started on October 17th. It's, let me go to it. So it starts on October 17th. It's basically 2 sets of 9 weeks programs. The first part is like more like software engineering skills, and then the second part is like specifically data engineering skills. So, and the cost, like I come from boot camp background, so to me the main thing I wanted to change when I started a boot camp was that you don't have to quit your job. Like I don't see the point. I don't see why you need to. You can do a part-time program, and with like focused skill sets, right, we're able to keep it to a reasonable length. So the first part is essentially like almost like back-end web development skills, Python, SQL APIs, scraping, building data dashboards. And then the second part is, working with Docker, Kubernetes, right, Spark, that type of thing, Kafka. And this, right, will set you up for that data engineering position. And that's why, like I said, I wanted to provide the same benefits as a boot camp, but cheaper and better, honestly. So there's a job guarantee within 6 months of graduation, and then you can, see the syllabus as well. All right. So if you guys are interested in that, set up a time to talk with me. You can click like apply, and I'll get in touch with you. Or you can, set up a time to chat. And I really think it's the best thing is, we should just talk and see if it's a good match for you, and if it makes sense or if it doesn't. All right.
I really like what you're doing. I think it's a beautiful website, and I think the free samples you have there are really valuable. For me, like I said, I was recently on the job market, and I have a job right now, but I think when I would be ready to go back on it again, I would really want to work on my coding skills. This is exactly what I would want to do.
Yeah.
I know there's a lot of choices when it comes to like this material on there, and there's a lot of stuff free online, but I honestly, to have somebody that an instructor is really a benefit. I think it's worth paying for. So I really like what you're doing, and I'm gonna just, I'm gonna keep that. I'm probably not on the market for it right now, but something I might really need in the future. One thing I was looking for on the website I'd like to see is usually you want to see like the about, like some of the people behind it. I thought your story was really interesting, and yeah, you don't have an about,
I don't
the
have
people
anything.
behind
Yeah,
this.
yeah,
Yeah.
definitely.
I mean, the website's beautifully designed, and the material's right out front, which I really appreciate. I love how the material's all out front. I I would have liked to see an about tag, but that's it. I really like it.
Thank you. I appreciate that. Yeah. Cool. So yeah, it's 8:30. I'm happy to take a couple more questions if you guys have it. Otherwise, like I said, check out the meetup. I may have another workshop next week on this, but otherwise, like I host them fairly frequently. So do that. And then if you know anybody, interested in data science or thinking about that you think might be good for like a career like this, just tell them about the school if you think it might be a good fit for them, or tell them to reach out to me. And we'll see if it's good. If they, for the career requirement, like there's obviously like a technical interview, but what I'm assessing is just like, do I think you can successfully complete the program? And it's based on, this material and just seeing how you code.
Do you want to talk a bit about what background people need? Like I know, I have some younger cousins and stuff that I might direct this way, but I'd like, have an idea of what backgrounds necessary.
Yeah, so the idea,
Like, should they have already completed a computer?
There are no prerequisites for the course. So like what I'm doing, is if you go through this material, these 10, 11 lessons, then I'll have enough to go on to then like talk with, to what I'll do is I'll pair program with you or the person applying, and code along and basically just see like how you work through code. And I've been doing this. I've probably interviewed like over, I don't even know, maybe like 500 students over the years. Like I've taught about 350. So I think I've interviewed even more. So I have from there I have a pretty good sense, right? Because I've done the interview and then I've taught the students. So I have a pretty good sense from like a 15, 20-minute long coding interview how you'll fit into the class. And so far, like with this current class, everything worked out great. Like all the students have done really well. Like if a student like fell behind, it was generally like one topic. And the beauty of doing something part-time is I just met with them, in between sessions and caught them up, and they've been great after that. So, so the idea is, that, yeah, like there's not really prerequisites. I'm definitely not looking for like anything on the resume. What I'm looking for, and that's part of the reason for data engineering too, is because data science, unfortunately, like people, it's the way the job market is now, they are favoring PhDs and master's degrees, but data engineering, those requirements really aren't put up in front and center. So what I'm looking is like, okay, do I think you're going to complete this program, like get something from the way that I teach and from the labs, and be successful in the job market. And the way that I'm assessing that is really just like these like 12, like if you complete these 10 and like absorb the material, then I'll be able to go from there and see how you'll do.
All right, thanks. I mean, I thought the material was really great.
Cool.
I'll have to go here, signing out soon.
Yeah, no problem. All right, guys, thanks so much for showing up. Yeah, I'll have like check the meetup page if you guys are interested in other meetups, but really appreciate your engagement tonight. Have a good one.